So this topic is accuracy and precision, two words that are commonly used by physicists to describe measurements. On our key concept slide, it says here that accuracy describes how close the mean value of a measurement is to the correct value. I sometimes smile a little bit when I see the correct value because in real experiments, I kind of think to myself as if we get to know that because we often don't. But we pretend maybe that there is one, right? That there's an actual correct value we're trying to measure. Precision, on the other hand, has to do with how much a measurement varies due to random noise. So one of the issues in real experimentation is that measurements will vary from one to the next when they're done independently. It's maybe cheating if you just set the instrument to the same value it had before. That's not doing it independently. But sources of noise, I mean, it's probably impossible to describe exactly where it comes from, but it's anything that's going to influence the outcome of a measurement and possibly make it different. And it tends to be random and uncontrollable. Anyway, so we're going to get a little bit into the nature of like how measurements vary. Sometimes we refer to that as an error in a measurement, but it's something that's kind of endemic to measurements. It's not like errors aren't really mistakes in that sense in physics. And this maybe relates to what this next thing says. It says precision and sometimes accuracy can be represented by an error interval. So I've looked at different sources on this over the years, and many physics classes would say that we're going to use errors. In other words, we're going to say, hey, here's a measurement, and it's plus or minus this. That's something we're going to be commonly doing. It's part of the lab outcomes of this course is to look at that in some more detail in association with some actual measurements that we can do. And in most classes like this, I think professors will say, I've seen many of them say this, is that those error intervals represent the random error in that measurement, which in that sense is associated with how precise that measurement is. But sometimes there's also accuracy issues, which could be, so a common term that you might see there in the experimental side of this course and other courses is a systematic error, which kind of refers to like a systematic inaccuracy, you could say. And I have sometimes seen examples in the literature where physicists will also use an error interval to describe that. So in that sense, I've seen it sometimes said in an undergraduate course, oh, the rule is error intervals always represent precision, but I can tell you I've seen exceptions to that. So that's why I wrote this way. Particularly in particle physics, I've seen that quite commonly. Anyways, error intervals can be represented by an estimated uncertainty. So for me, when I say error, that really represents what is regarded as the uncertainty. So in some physics classes, you'll hear people talk about uncertainties. I've even heard of physics professors who would say, we don't make errors in here, we're just uncertain. But I don't know, slice things that closely or whatever. To me, they mean almost the same thing, but in that sense, the estimated uncertainty, if I say, hey, I've done a measurement, maybe it's like 90 centimeters plus or minus a centimeter. I would say the estimated uncertainty in that case is 1 centimeter. In other words, the number that was plus or minus. So that's kind of how I'm meaning this language. There's error interval and there's uncertainty, but I sometimes will also refer to uncertainty as the error. I feel like those two things are interchangeable. Now, before we move on, I have here a picture of what I think is kind of like an archery analogy to accuracy and precision that has often helped me to remember the difference between the two. And maybe some of you may already know, I think I did an earlier example that involved some archery. I used to be an avid archer. I haven't done it in many years, though, I have to admit, but used to be really into it. So it makes sense to me. And most people understand the bullseye, right? So like, let's say this is a target with a bullseye right here, and somebody took like 5 arrows to try to get that bullseye. And I would say, so this doesn't look so good, right? These arrows are obviously quite scattered around this bullseye, but I described this one as accurate because it's not really like the arrows are more often or by much more like above or below it or to the right or to the left. They're kind of randomly scattered around the bullseye. So this person was accurately aiming at the bullseye. In other words, the mean value is probably pretty close to a bullseye. In that sense, mean value being close to the correct value. The correct value here is a bullseye, right? So the shooter was accurate here. The archer was accurate. Contrast that to an archer who is precise but not accurate. I tried to fit in 5 little arrows, pictures of them here, but they kind of overlap a little bit, so maybe hard to see all 5 of them there. But there's a really tight cluster there, which represents a high level of precision. In other words, the amount of variance between one shot to the next due to random noise effects, like maybe just random differences in how the archer released the error in this case, which in a physics experiment is maybe random differences in how the measuring instrument got used that are really unavoidable. You can't be perfect enough to get rid of them entirely, but you can improve, right? You can try to get as close and close, just like the archer can improve, right? This archer obviously was very, very precise, but not accurate, which is maybe not ideal. The ideal is to be accurate and precise, of course, for archery. And one could argue that that is also true in physics. This is also what we would like to achieve. But these issues come up. Like you'll see some experiments where you're maybe more in this domain where things look pretty accurate when you check it out, but there is statistical error. Actually, this is the easier one to deal with. So we'd like to see this one more often because usually these kind of results, we can handle it mathematically. This actually tends to happen commonly in experiments in this class over here where we claim a high level of precision and things still don't work. So we wind up seeing this one a lot, but it's not necessarily the ideal. So anyways, we're going to look at some examples now that check out these ideas a little bit more in the context of experiments.